This video begins on page 11-17 in your note packet, and it discusses Dalton's law of partial pressure. So when we combine gases that don't react, Dalton's law of partial pressure tells us that the pressure of a mixture is going to be equal to the sum of the individual partial pressures. Now, this only works when they don't react and you just have these gases floating around in the same container. So this tells us that the total pressure can be thought of as the pressure of gas A plus the pressure of gas B, C, and D, and so on. So the simplest type of problem that you might have seen in your introductory chemistry classes looks like this. What's the total pressure if you have helium at 1.5 atmospheres and oxygen at 2.0 atmospheres? Well, the pressure total is equal to the pressure of the helium plus the pressure of the oxygen. So that's equal to 1.5 atmospheres plus 2.0 atmosphere. So the total pressure is equal to 3.5 atmospheres. And Dalton's law of partial pressures really is that easy. You don't have to get all fancy, you're just adding. The applications of the partial pressure law can get a little bit fancier where you have to go back and do something else. Okay, let's look at another problem. This time we're kind of going backwards. How many grams of oxygen are present at 25 degrees C in a 5-liter tank with a total pressure of 30 atmospheres, with nitrogen present in the tank at 15? Well, we're trying to find out the mass of oxygen in there, so the way we start this is to first find out, using Dalton's law, what is the pressure of the oxygen. Then we can go do something else with that information. So we know that the pressure of the oxygen is equal to the total pressure minus the pressure of the nitrogen. That's information that was provided in the problem. So that's equal to the total pressure, 30 atmospheres, minus the oxygen's pressure, 15 atmospheres, is equal to the pressure of the oxygen minus the pressure of the nitrogen, is equal to the pressure of the oxygen, which is also 15 atmospheres. So now I use Dalton's law, and now I'm going to go do something else with that. That something else is to try and figure out how much oxygen I have in there. So now I know that the oxygen's pressure is 15 atmospheres. I know that the temperature is 25 degrees Celsius, which is 298 Kelvin. I know that the volume is 5 liters. So now I can use the ideal gas law to find the number of moles of oxygen, and from the moles I can find the grams. So N is equal to PV over RT. Our pressure is 15 atmospheres. We only use the pressure of the oxygen, not the total, times the volume, 5 liters, divided by the gas constant, 0.0821 liter atmosphere per mole Kelvin, times 298 Kelvin, and that's equal to 3.07 moles of oxygen. So now I've used Dalton's law for the first part of the problem. Now I use the ideal gas law. Now to answer the question, how many grams of oxygen, I'm going to use stoichiometry. 3.07 moles of oxygen. We know that the molar mass is 31.9988 grams of oxygen per 1 mole. So the answer is 98.2 grams of oxygen. On the next page, there's a problem for you to try on page 11-18 in your notes. So why don't you pause this video and go ahead and try this problem. And then after you've completed the problem, you can come back and look at the solution. So a diver wants to fill a tank with oxygen-enriched air. So he puts in 50 grams of oxygen and 150 grams of nitrogen, holds the tank at 25 degrees. What's the total pressure? Well, we're going to figure out the pressure of each one, and we can add them together. And there are a couple of ways you can do this. Since we know that the total pressure is equal to the pressure of each one because they all act the same, you can actually solve the ideal gas law twice and add the two pressures together. Or if you're as lazy as I am, you can actually figure out how many moles of each gas you have, add those together, and then just do the pressure calculation once. And that's what I did in solving this problem. So I know my volume is 4.00 liters. I know my temperature is 298.2 Kelvin, changing Celsius to Kelvin. And we know the mass of each of these gases. So we have to start converting grams into moles. So 50 grams of oxygen. I know that 1 mole of oxygen has a mass of 31.9988 grams. And so that's equal to 1.56 moles of oxygen. I do the same thing for the nitrogen. I have 150 grams of nitrogen. And I know that 1 mole of nitrogen gas, which is diatomic, has a mass of 28.01348 grams. So that's equal to 5.35 moles of nitrogen. Now, we could use the ideal gas law, solve for the pressure of each of these, and then add those pressures together. Or what I did was just added my moles together. When I add this together, I get 6.91 moles total. And I solved for the pressure using the total moles, so I only had to use the ideal gas law once. nRT over V. You could do it either way, you get the same answer. 6.91 moles times 0.0821 liter atmosphere per mole Kelvin times 298 Kelvin divided by 4.00 liters is equal to 42.3 atmospheres. So we can solve a lot of different problems just by thinking about what we've done. I think one of the challenges in Chemistry 111, whether you're doing gas law information or any of the other topics, is that a lot of times in class we show examples of how to use information, but then some of the problems you really have to think back and put it all together and combine multiple pieces, and that's where the challenge comes in. Now, related to Dalton's law of partial pressure, we start to introduce the idea of a pressure fraction as related to a mole fraction. The mole fraction is defined as X. We call it X sub A. That's equal to the mole fraction of A, and it's the number of moles of gas A in a mixture divided by the total moles. Because these are fractions, all of the mole fractions add up to 1. So if you have a bunch of gases, gas A, the mole fraction of A plus the mole fraction of B plus the mole fraction of C, if I had 30 gases, I'd have 30 mole fractions, but it adds up to a mole fraction of 1. And that makes sense because if we think about percentages, if I multiplied this by 100 to make percentages,